In today's lecture, we will try to understand some properties of the geospace. Since the state of matter which exists in this geospace is primarily plasma, what we will do is we will try to understand, to begin with, what is plasma, and we will not go into the details of understanding the behavior of plasma. Rather, we will try to understand how is it different from other states of matter, and then some basic properties of plasma. Okay, why do we need to call this particular state of matter as a separate state, as a plasma state? So some basic properties of plasma. And plasma as a whole, how does it behave? And then we will look at some characteristic parameters which are associated with plasma, or the behavior of plasma, or the motion of plasma. We will try to derive some simple expressions for things like what is gyro frequency, what are plasma oscillations, and then we will try to see what are plasma waves, etc. Okay, so this is going to be the topic of discussion for a couple of lectures from now. Okay, now answering the basic question, what is plasma? Plasma is considered as the fourth state of matter. Okay, all of us know very well that what a state of matter is. State of matter can be defined as a physical state, physical manifestation in which matter or the substance appears or manifests itself, right? So states of matter that we are very familiar with are simply the solid, liquid, and a gas, right? So all these three states of matter are probably like solid is when you have more number of atoms or molecules tightly packed within a small volume. Liquid is when you have lesser density in comparison to solid, and gas is when you have even lesser density when in comparison with liquid, right? Now, the point is, plasma, apart from these three, is defined as a separate state of matter. Okay. Now, this course is called as the solar terrestrial physics, right? So this is the solar terrestrial physics course. We will try to understand all those physical phenomena which happen between the sun and the earth. So earth is a terrestrial planet, right? There are other terrestrial planets. So earth is a terrestrial planet. So solar terrestrial physics refers to the understanding of the phenomena which happen in the terrestrial atmosphere but are primarily driven by the solar forcing, right? Now, in this terrestrial atmosphere, we know it for a fact that we have an atmosphere, of course, right? We have an atmosphere which is basically a gas envelope which is surrounding the earth and bound by the gravity. When you move to the upper altitudes, let's say 50 kilometers, we are going to realize that at these heights or at these altitudes, the state of matter is not neutral gas, rather it is existing in a state which is called as plasma. So plasma being defined as the fourth state of matter, but if you want to understand what exactly is it, it is just a gas which has electrons and ions in addition to neutral particles, neutral species, let's say. Okay, this is the plasma. So, plasma has electrons, ions, and some neutral species, because of which, although it is a fluid, because of which we are not going to call it as a gas or as a liquid. We are going to call it as plasma. That's it. Why? Because of the presence of electrons and ions, this plasma behaves like an electrodynamical or electromagnetically active entity. So, because of these electrons and ions, plasma gets influenced by the presence of magnetic field or by the presence of electric field. Okay. So, that means the motion of plasma from one point to another point will be under the guidance of magnetic and electric field, or can be changed from one point to another point by applying electric and magnetic fields. Right. Now, where have we understood the electric and magnetic fields? We have seen that when there are particles, charged particles, these charged particles will get influenced by the magnetic field. They will also get influenced by the electric field, because if you keep a magnetic field and if the particle has some velocity, the particle move in a certain way. And if you have an electric field, the particle will move in a certain direction, right? That means you are giving this behavior to the macroscopic entity of the plasma itself. Now, coming back to the relevance of solar terrestrial physics, we have to understand plasma or the behavior of plasma or the physics associated with plasma, because we have to understand the upper atmosphere, which is basically called as ionosphere, which is basically called as the ionosphere. What is ionosphere? Ionosphere is the region of the Earth's upper atmosphere where plasma is the primary state of matter. Okay, plasma exists in a large numbers. Okay, now what are we going to do in this lecture is that we will try to understand some basic properties of plasma, and most importantly, 99% of the matter in the visible universe is existing in the plasma state. Okay, 99% of the matter is existing in the plasma state. And even if you look around, you will find many places or many manifestations of plasma in different technological or electronic devices. But nonetheless, for the case of discussion in this course, when we have to understand ionospheric phenomena, we have to know the basic constituent of the ionosphere is electrodynamically active. That is why we get to see so many interesting aspects in the ionosphere. Okay, so 99% of the uh, matter in the universe, in the visible universe, is existing in the plasma state, or we can say that it is existing in the form of electrons, ions, and neutral species. So, starting from the surface, we can encounter plasma in the ionosphere. We can encounter plasma where and all you can find plasma for relevance to this course. We can find plasma in the ionosphere. We can find plasma in the radiation belts. You can read about these things if you have done any earlier course in atmospheric and space physics. You may have already heard about these places, but nonetheless, you can, out of curiosity, you can read about these things and find out how is plasma the main state of matter in these places. So we can also find plasma in solar wind. Okay, and even the star, the sun, is just a huge bubble of plasma, hot and energetic plasma. Okay, now in day-to-day life, we do encounter plasma in few places. Let's say in fluorescent neon signs or etc. Okay, in reactors, many places. Okay, so it appears that we are living in a very small percentage or very small that 1% of the universe where plasma is not naturally occurring. Okay, so these places, solar wind, ionosphere, radiation belts, all these places are where plasma occurs naturally. It's there. Okay. But in the ionosphere, of course, we don't live in ionosphere. On the surface, plasma doesn't occur naturally. So we live in a very tiny fraction of the universe where plasma is not occurring naturally. Wherever you go, you will find plasma naturally. Okay. Right. So this is the basic definition or basic introduction to plasma. Okay. Now plasma can be produced. How do you produce plasma? Plasma can be produced in two different ways. One, at very large temperature. Number two, at very low pressures. These two are the favorable conditions for the existence of plasma. Okay. Either at very large temperatures you can find plasma, or you can, at very small uh, values of pressure you can find. So plasma also has one more very interesting property, which is called as quasi neutrality. It is very easy to understand what is neutrality. Now that I am mentioning plasma is an entity where there are there are many number of free electrons and ions. We know that the electron, the charge is negative, and for the ions, the charge is positive. So if you have an atom, and if you remove the outermost electron, it will become positive. It will become a positive ion, and the free electron that you have removed is the electron. Now, in addition to this, it has in plasma, the fundamental definition of plasma is that the number of electrons is always equal to the number of ions. So the total negative charge is always compensated by the total positive charge. So if you have Ni number of ions per unit volume, okay, and if each of the ion has Q charge, Niq is equals to Neq. So this is about the total. This is about the total numbers, and this is about the total charge being conserved. In addition to this, there are neutral particles, neutral species as well. Quasi-neutrality refers to the macroscopic maintenance of charge neutrality, can be simply referred to as quasi-neutrality. And in addition to what a deviation to this macroscopic word involves a detailed discussion. We will go there after certain period of time. Right. In addition to this, plasma also behaves collectively. So this is the collective behavior of plasma. What does it mean? So plasma behaves as a single entity when it is subjected to electric or magnetic fields. Okay. So these are basic properties. So each of these topic can be discussed independently for a lengthy discussion, but we are not doing that because there are other courses where this information is readily available in detail. If needed, you can always refer to those courses, those lectures which are available on the NPTEL platform itself. But what we will do is we will briefly cover those things just at the very basic level of concept. Okay. So now let us say if we consider any neutral gas without the presence of any charged particles, since the molecule is neutral, there is no net electromagnetic force on it. So the force that can act on it is only the gravity, which is very negligible, right? And the molecule moves undisturbed until it collides with the other molecule. But when you have an ion, okay, so if the molecule is moving freely and if it collides, so the collision will alter the movement of this molecule. So the collisions are controlling the way these molecules, the neutral molecules or neutral atoms, will move from one point to another point. Okay. Now the point is when you have charges, the controlling factor or controlling influence can be electric or magnetic fields. Okay. So in the case of plasma, it is very different. So as the charged particles are moving around, they can generate local charge densities. That means they can create electric field. Let us say if you have more number of electrons in a particular place. So that means An electric field will be generated because of this charge non-maintenance of the charge neutrality. Local electric fields will be created, and electric field will always be created in such a way that the electron has to move opposite to it, and the movement of electron is only to compensate this electric field, right? So the motion generates currents, and when there are currents, there will be magnetic fields, right? So because of the presence of electrons and ions, we can have all sorts of electromagnetic phenomena occurring within plasma. So plasma, if you don't talk about electricity, magnetism, electric field, magnetic field, all that, is simply a gas which has sparsely distributed electrons and ions along with some neutral species. Now, depending on the temperature, the density of electrons and ions may always change, but that's it. It's a fluid. It's a gas, right? But it's a gas where movement of electrons will generate electric fields, electric currents, and these currents can subsequently generate magnetic fields, etc. Okay, so we have to treat plasma as an electromagnetically active entity, right? And more importantly, in plasma, the idea of temperature is slightly different because temperature, right, like we know, is an average, is a measure of the average energy that is possessed by a molecule or an atom. It is a parameter which defines how much energy, how much thermal energy does the particle or the molecule possess, right? Now, in plasma, we do not use the unit of Kelvin for temperature. Rather, we will use the unit of electron volts for denoting temperature, right? Now, we know that the average kinetic energy along 3 degrees of freedom, so E average is approximately is 3 by 2 kBT. What is kB? kB is the Boltzmann's constant, right? And which also says along 1 degree of freedom, the average kinetic energy is 1 by 2 kBT. So the energy and temperature, you see this energy and temperature are very closely related. The only bridge that is in between is the Boltzmann's constant. So we will not use temperature in the units of Kelvin, but we will use the temperature in the units of electron volts. Okay, so in plasma, we will not get confused about the number of degrees of freedom that is involved. We always use energy corresponding to kBT. kBT. Okay, so let us say kBT is 1 electron volt. That is, energy is 1 electron volt. Okay, so how much is it? 1 electron volt is 1.6 10 to the power of minus 19 joules. Right. Now, if you calculate the equivalent temperature of this energy, it would be 1.6 10 to the power of minus 19 divided by 1.38 10 to the power of minus 23, which will give you 11,600. Okay, what have you done? You have divided joules with kb or kb, right? So what you get is simply T is equals to 11,600 Kelvin. So temperature T for 1 EV is 11,600 Kelvin, which means every time we have to use a number of, let's say, 11,000 Kelvin, we can simply say that the temperature is equal to 1 EV. Why do we do this? Because in plasmas, the temperatures are very, very large. It can go from several hundreds of Kelvin to several thousands, hundreds of thousands of Kelvin. Okay, that's why we will not use those big numbers. Rather, it is easy to convert them into electron volts and say that the temperature of this particular plasma is this many electron volts. And another important aspect is that we are always used to the idea that the temperature is just is an average measure of the molecular energy in a given gas, right? And we never bother, if it is a mixture of gases, we never bother to define temperature for each of the gas in the mixture. But in plasma, it's not like that. Plasma, the temperature is not same for all the species. So we define temperature for ion, temperature for electron, and temperature for neutral species. Why? Simply put, if there are enough number of collisions, each molecular atom will get enough opportunities to transfer its energy and maintain a thermal equilibrium. And if it goes on in the entirety of the gas, you can establish a thermal equilibrium, and that equilibrium temperature is the temperature that you are referring to. But in plasma, maybe because of the lesser densities, the electron temperature, ion temperature, and neutral temperature are treated differently, right? Now, these are basic properties of plasma. So, if you write gas equation, P is equals to N Kb T. In the case of plasma, you have to write Ti plus T. This is how things change. So, plasma. So, we have seen what is plasma. Fundamentally, how do you define plasma? Why do we need to understand about plasma? Because plasma is the state of matter in the geospace, between Earth and the Sun, the space or the around the Earth within the magnetosphere. The state of matter primarily is in plasma. Why is it in plasma? Because solar radiation is energetic, and this will ionize atoms and molecules and create plasma. And the solar wind, which is traveling from the Sun towards the Earth, is also in plasma state. It is highly energetic electrons and ions which are coming away from the Sun. So that is why we need to have some understanding of plasma. So the basic idea is to introduce those aspects, those properties of geospace. So how is it different? So what we have done is plasma. We have defined what is plasma, which is just the fourth state of matter, and we have intuitively understood how is it different from the other states of matter, right? And we have seen some properties of plasma, not many, some, like it is neutral in nature. It is it exhibits what is called as the collective behavior, and we will look at gyro frequency and plasma oscillations in the next lecture. But in this lecture, we have just been able to see what is plasma and how is plasma different from the other states of matter.